In this video, I want to look at how we use the subgroup criteria theorem to prove a particular subset of a group is in fact a subgroup. And we're going to start, of course, by looking at what the theorem actually says. This theorem says that if G is a group and H is a non-empty subset of G, then H is a subgroup of G if and only if H has this bizarre looking property. And this property basically says that if I take any two elements inside the subset H, that this funny looking product A times B inverse will belong to H. The way we use this theorem to show that H is a subgroup is that we first of all verify that H is a non-empty subset. We then show that H has this property. The backwards arrow of the theorem kicks in, and we get to conclude that H is a subgroup of G. In other words, this is what our strategy looks like. We will first of all pick A and B to be arbitrary elements of the set H. Then we have to find B inverse inside the group G. Then we will compute the product A times B inverse inside the group G. And this is being done inside group G because H, of course, is a subset of G. Once we have A times B inverse computed, we then show that A times B inverse satisfies the membership rule for H, and so it belongs to H. And it's at this point that we can then say H is a subgroup of G by the subgroup criterion theorem. So anytime we want to use this theorem to prove something is a subgroup, this is what the strategy is going to look like. Now what I want to do next is I actually want to look at a specific example to see how we do this theorem in a particular concrete example. So here's my example. I'm going to define the set SL2 to be the set of all 2 by 2 matrices such that the determinant of that matrix is known to be equal to 1. Now this says that SL2 is a subset of GL2 because GL2 is the set of matrices that have determinant not equal to 0. And I also want to recall that GL2 under its multiplication is a group. So the question is SL2 a subgroup of GL2? Well, I want to first of all note that the identity matrix belongs to SL2 since the determinant of the identity matrix is known to be 1. And that's enough to put it in SL2. But the important thing is that says SL2 is not the empty set. So the next thing that I do is I pick two arbitrary elements of SL2. I am going to let A be the matrix A, B, C, D, and I'm going to say that he's in SL2. So I know that the determinant of A, which is AD minus BC, is going to be equal to 1. And I'm going to let B be the matrix EFGH, and I'm also going to assume that he is in SL2. So the determinant of B, which is EH minus FG, is also equal to 1. So I've now got my two arbitrary elements of SL2. The next thing that I need to do is I need to find B inverse inside GL2. So B inverse inside GL2, the way, well, let's first of all write down B. So B is EFGH. And he is inside SL2, which puts him inside of GL2 because SL2 is a subset of GL2. And inside GL2, an inverse of a matrix is formed by looking at H over the determinant of B, and this will be minus F over the determinant of B, and this will be minus G over the determinant of B, and this entry will be E over the determinant of B. And let me clean up that bracket there. And so this is B inverse. Now recall the determinant of B is equal to 1, so they all drop out, and we are just left with B inverse is going to be H minus F minus G and E. And this is B inverse inside GL2. Now what I need to do is I need to compute A times B inverse. Well, A is A, B, C, D, and B inverse, we just got done computing him. He's H minus F minus G, E. So when I compute this matrix product, I'm going to get AH minus BG, and here I'm going to get minus AF plus BE, and down here I'm going to get CH minus DG, and over here I'm going to get minus CF plus DE. So I've got that matrix computed. The question now is A times B inverse inside SL2? Well, to figure that out, I need to take the determinant of this matrix. So the determinant of A times B inverse is going to be, well, let's see, it's going to be this product minus that product. So I want to write that out. So I'm going to have AH minus BG times minus CF plus DE, and then I'm going to subtract off minus AF plus BE times CH minus DG. And there's a lot of computation that we have to do, and I want to go ahead and do it fairly carefully so that you can see how it gets done. I need to distribute these two things out, and when I do, the first one is going to be, let's see, I'm going to have AH, actually I'm going to have a minus sign, so let me start over. We're going to have this guy times that guy, so we're going to have minus AH times CF minus a minus BG times CF, and then we're going to have a plus AH DE, and then we're going to have a minus BG DE. And that's this product. Then we have a minus sign, and now I have that product. And I'm worrying about that minus sign afterwards. And so when I look at this, I'm going to have minus AF times that CH. So I have minus AF times CH, and then I'm going to have plus BE times CH. And then I'm going to have a minus AF times DG, and then I'm going to have a minus BE times DG. Now what I want to do is I just want to kind of clean things up and in particular deal with this minus sign. So when I do that, what am I going to be getting? Let's see, the determinant of A times B inverse is going to look like this now. We have minus AHCF plus BGCF plus AHDE minus BGDE. And then I've got to do the minus sign on all of these. So we're going to have a minus AFCH minus a BECH minus an AFDG minus a minus BEDG. And now it's a matter of seeing what I've got and what will cancel each other out. And what I notice right away is that I have a minus ACFH and another positive ACFH, so they add together and form a 0. And down here I have a minus BGDE, and this is a plus BGDE, so they're also gone. And what's left looks like this. We now have BGCF plus AHDE minus BECH minus AFDG. And what I'm going to do is I'm going to gather the A's together. So I have an ADEH from this term minus an ADFG from this term over here. And then I'm going to gather the B's together. And I have a BCFG from this term here minus a BCEH on that term right there. Now what I can notice is that I now can factor out an AD out of those two terms and a BC out of these two terms. So that's the next thing that I'm going to do. So we have an AD times EH minus FG. And over here we have a BC times an FG minus B, not minus B, minus EH. And what I want to notice is that the stuff in the parentheses are almost matches, but this one is the additive inverse of that one. So I'm going to factor out a -1. So I'm going to write this as AD times EH minus FG minus BC times EH minus FG. And what I'm now looking at is I can factor out the EH minus FG, and when I do, I'm left with AD minus BC times EH minus FG. And what I want to remember is that the determinant of A was AD minus BC, and that was equal to 1. So this first thing is equal to a 1. And the determinant of B was equal to EH minus FG. And so this second thing is also equal to a 1. And so I get that that product is equal to a 1. So what the upshot of all of this is that the determinant of A times B inverse does turn out to be 1. So we've now shown that the determinant of A times B inverse is equal to 1. And so what that says is that A times B inverse is indeed inside SL2. And so we have shown that if A and B belong to SL2, then A times B inverse belongs to SL2. And so I could now say that SL2 is a subgroup of Gl2 by the subgroup criterion theorem. And it's worth noting that SL2 is called the special linear group of order or size 2.